let's talk about a one sample z-test and how you can tell it's a one sample z versus t. So let's talk about the details here. According to the a government survey, the daily one-way commuting distance of U.S. workers averaged 13 miles with a standard deviation of 13. By the way, that should, it should raise some hairs on the back of your neck or something. Like, wait, how do you have an average of 13 and a standard deviation of 13? Well, it's lots of variability and likely some skewness, right? That the people that have super long commutes that are actually skewing this out and making the standard deviation much higher, okay? So commuting distances are obtained, back up. A researcher wants to know if this is applicable to the LA area, like i.e. do LA workers drive more or less than the average? Commuting distances are obtained for a random sample of 169 workers in LA, and the sample mean distance is found to be 16 miles with a standard deviation of 13. So test the hypothesis assuming alpha equals 0.05 and use the 7 steps. So what are the things to sort of note here, the things that are likely to be important? So as you read this, according to a U.S. government survey, the daily one-way commuting distance of U.S. workers averages 13 miles. All right, so if it's average U.S. workers, we're talking about a large, massive amount of people. So that's referring to the population, right? There's an average U.S. workers, so we're talking about a population, which means that the population has a mean, a mu, equals 13. Right? So it gives us the population mean. So the commuting distances of U.S. workers averages 13 miles with a standard deviation of 13. So it's also giving us, for the same U.S. group, the standard deviation of the population. So because of that, it's giving me sigma. Sigma equals, it's also 13. Okay? So we have our population mean and a population standard deviation. As soon as you see that we have a population standard deviation, that should clue you in that this is likely a one sample z-test, because we're actually given the population value and we need that to do a z. Okay, so what else are we given? The researcher wants to know if this is applicable to the LA area. Commuting distances are obtained for a random sample of 169 workers. All right, so now we're talking about a random sample. So in our sample, so this is here's our population stuff up here. Our sample, let's write it over here. Our sample has an n equal to 169 people in our sample. And the sample mean distance is found to be 16 miles. All right, so our m equals 16. And then it says with a standard deviation of 13. So also we have an s of 13. Now, this is where a problem like this is maybe trying to trick you, okay? Because you're given the population value is 13, you're given the sample value is 13. You may be thinking, oh, well, I have s, so I should maybe do a t-test. So the fact you have s, in this case, is irrelevant. I mean, it's cool, you know it, but we have the population, so we're not going to try to estimate the population with this, even though it's the exact same number. I'm not going to try to estimate the population because I already have it. So normally I would use s to estimate sigma, but because I already have sigma, I don't need to do that, so I'm not even going to bother with this at all. This is not even going to come into play. All I really need is that the sample has a mean of 16, the n's 169. The rest of it I can do as a one sample z-test. Okay, so those are the important things. I got the population values, I got my sample information, I can now do the rest of the test. Now, notice here that it says, if I'm trying to figure out the null and alternative, so here's my step 1, step 2. So it says up here, a researcher wants to know if this is applicable to the LA area, and it says in parentheses, do LA workers drive more or less than the average? So more or less tells me that this is not a directional test. All I want to know is the mean based on this test not equal to 13, right? So this is looking at like a two-tailed test. So if that's true, then the null is going to be that mu is equal to 13. Okay, so that's what we're trying to test. Is our sample of 169 commuters different than the population. Step 3 is to, remember 3 and 4, yeah, 3, I think 3 is the sort of state alpha. It says here alpha is 0.05, so we already know what it is. What's the kind of test? Well, again, because we know sigma, this is a one sample z-test. It also helps that it says it right there. But, you know, it may not always say that, like if you're doing a test or something, it may not just tell you it's a one sample z. How do we know? Well, if sigma is there, if you're given the population standard deviation, you can do a one sample z-test. Okay? Step 5, we need to know the critical value and state a decision rule. So for that, we got to think about this for a sec. Alpha is 0.05, right? So thinking about this again, we need alpha is 0.05. So I need to split alpha up into 2 pieces. I need there to be 2.5% up here and 2.5% there, right? In order for it to be a two-tailed test with alpha equals 0.05. So I need to find a value in the z table that corresponds to roughly 2.5%. So for that, I'm going to go to my handy z table, which is over there. Go back up to z for a second. And I need to, in the smaller portion column, I need to find a value that corresponds to 0.025. So far I haven't gone far enough yet. 0.025 is right here. So this is my smaller portion. So it looks like my critical value, my z critical is 1.96. 1.96. That should sound somewhat familiar. It's the same, we talked about this in lecture before. That's the number that comes up. 1.96. So my z critical, sort of two-tailed, equals 1.96, but really it's a plus and minus 1.96. I need a 1.96 on the positive side, and I need a negative 1.96. I need both of those. So it's going to be a plus or minus 1.96. That being said, my decision rule is going to be, you know, if my z observed is greater than, I even say the absolute value of my z observed is greater than 1.96, I'm going to reject the null hypothesis. Okay? Pretty straightforward. So the nice thing about using z-tests is that there's not a different z-critical for every degree of freedom. It's the same. 1.96 is the two-tailed value for z. Right? It doesn't change because of degrees of freedom or anything. All right, so now we need to go to step 6. Let's see, I'll do step 6. Yeah, let's do down here. Step 6 states I need to do my actual test. So my z observed equals to my mean. I keep wanting to put x bar. My mx minus my mu over the standard error of the mean based on sigma. So this is, so we said it was 16. 16 minus 13, that's my sample minus my population value. This is the standard deviation over the square root of n. That's what gives us our standard error. So we have our population standard deviation of 13. I have 169 commuters. So to get my sigma sub m, I need to take my sigma over the square root of n. In this case, that ends up being 13 over the square root of 169. So the square root of 169 square root is 13. So this ends up being 13 divided by 13 equals 1. So my standard error of the mean equals to 1. All right, that's pretty straightforward. So this is that same, I'll just write it here just so it's clear, so we'll cut off there. That this ends up being my 13 divided by the square root of 169. All right, it ends up being 16 minus 13 is 3. It was 16, right? 16? Yeah. Minus 13 is 3. So I'm going to divide that by 13 divided by 13 equals 1. 3 divided by 1 is 3. So my z observed is 3. So I can go now to step 7, my decision rule. Since 3 is larger than 1.96, I'm going to reject the null. So there is some evidence that LA drivers going 16 miles commute, that our LA drivers drive a significantly different amount. In this case, it's higher, drive more than the average U.S. Population. Okay, and that's it. Since our z observed is larger than our z critical, we're going to reject the null. The null said that it's equal to 13. We're saying nope. We rejected that idea. It's probably not equal to 13. It seems like in LA it's actually higher, significantly higher than 13 relative to the population value. All right. Hopefully that's pretty straightforward. That's probably one of the easier of the hypothesis tests because, you know, the population value is given to us, so it's pretty straightforward. We don't have to use, you know, t-tables and look at different critical values. They're pretty well known. If you remember that a two-tailed z is 1.96, a one-tailed z is 1.645. Those numbers typically don't change. As long as alpha is 0.05, those are the critical values that are relevant to a z-test. 1.96 for a two-tailed, 1.645 for a one-tailed.